So we're gonna pick up where we left off. Last week, just before the semester test, we started discussing the priority queue ADT. We said that unlike the other ADTs we've discussed thus far, this one stores key value pairs instead of just a single element. The keys can then be prioritized, which allow us to extract whatever element has, or whatever key value pair has the highest priority according to that key. Right. So our entries now look like this. They're key value pairs. And our methods now are insert kx, which would be value x with key k, and remove min, which returns to us the key value pair with the highest priority. And we've chosen the convention that that will be the one with the minimum priority. So remove min is our function. We then look at the fact that to be able to actually determine from a collection of keys which has the highest priority, we need to be able to compare them in some way. We talked about how a total order is necessary over those keys, and we would need a comparator that then encapsulates that action. So a comparator that allows us to be able to compare two keys and to be able to determine from that which of them is smaller than the other, to be able to actually find a minimum over a collection of keys. So this comparator, when given two keys, would return integers such that I is less than 0 if A is smaller than B, I is equal to 0 only if A is equal to B, and I is greater than 0 if A is greater than B. And of course, if A and B can't be compared, then we can't actually calculate what I should be, because we can't tell which is greater than the other. And so we should throw an error if that happens. Now we see that we could actually sort a list of elements using a priority queue. How would this work? Well, if we were to insert into our priority queue a collection of elements, or some set of elements, and then to call remove min n times to remove those n elements from our priority queue, each time we would actually be removing the one that has the current highest priority of those that are left in our priority queue. And that means we're actually returning them in order. Even though we can put them in any arbitrary order, each time we call return min, they'll give us the next highest priority. And so we could actually sort an entire list of elements if we were to store the values as our keys. All right, so with certain elements one by a series of inserts, then we'd remove these by calling remove min n times to remove our n values that we've stored within this priority queue. And what we'll see is that the running time of this actually depends on which implementation we use for our priority queue. We haven't looked at any concrete implementations yet, but we'll find that the two methods, insert and remove min, depend on that implementation. And because this way of sorting depends on calling those two methods n times, it will depend on the runtime of those two methods. And we call this priority queue sorting. So sorting using a priority queue rather than the methods we've learned up to now. We've already discussed insertion sort as one sorting method, and we certainly should be familiar with others like quicksort, merge sort, and so on. So on the right here, we have an algorithm that describes what should be done. Inputs will be a sequence S. I will then use our priority queue P with a comparator C, so some ability to be able to compare these elements. Then our output should then be the sequence S now sorted, so in increasing order according to that comparator C. There are two steps. First, we empty S into our priority queue. So as long as S isn't empty, we're going to remove first, right? These aren't in a particular order, so just remove the next item from the sequence and then insert into our priority queue. Again, that doesn't put it in order. The priority queue simply stores, well, actually it really depends on our implementation. But regardless, we're simply inserting them arbitrarily into this priority queue. Then we empty them from the queue using remove min. Now we're actually getting them in a specific order, and we then insert those back into the sequence S, and they will now be in order. All right, so let's look at concrete implementation. We could implement a priority queue using a linked list, very familiar with that concrete data structure. And depending on how we store the elements within that linked list, that will determine how much time our insert and our movement takes. So for example, if we were to implement it using an unsorted linked list, as in each time that we insert, we simply add it to the end of our linked list. We know that that will be constant time, but we could also be adding it to the front. Regardless, this will take constant time as long as you have a reference to that tail or the head, and we aren't concerned with what order it will be in. And so each of those take constant time. Altogether, the total time for those inserts, we can be able to easily calculate would then be order n, because each one is constant time. However, then our remove min would take order n time, right? We'll also discuss now, including that discussion, the min method, which simply returns just the minimum without removing it. Regardless, each of these would take order n time. Why? Because we have an unsorted list. And to find a minimum in an unsorted list takes order n time. We'll remember our usual algorithm finding a minimum. We start at the beginning, assume that that initial one is our minimum, then traverse the rest of our list, each time checking is the current value less than our minimum and updating our minimum where necessary. That will take order n time because we have to do n comparisons to be able to do that. All right. And so overall, we're actually going to have a quadratic function because we're going to be doing n constant time operations followed by n linear time operations. So all in all, that would be quadratic time. If on the other hand, to keep our list sorted at all times, then each time that we insert into that list, we'll have to do worst case up to n comparisons. Granted, we realize that the initial insertion will only have a single item, so it'll already be sorted. Then when we enter the second item into that, we'll have to compare it with the first to make sure those stay in sorted order. Then the third has to be compared to the first and the second, the fourth with the first to the third, and so on. At the very end, when we insert our nth one, it will have to be compared with all the other n-1 ones and inserted at the correct position. So we're always keeping our priority queue sorted, which means that our inserts are now worst case order n. However, if we're keeping this priority queue sorted at all times, then calling remove min will be constant time. Let's say, for example, we sort them in ascending order, then that means the minimum will still be that which is at the front of our list. And so remove min can now be executed in constant time. We see that if we're doing n inserts that take worst case order n time, then altogether that would be an order n squared method, just that part of it. And then we're going to do n remove mins to remove all elements in order. Each of those are constant time. However, altogether that will be order n time. If we have a first step that's quadratic time and a second step that's linear time, overall our method is quadratic, or rather runs in quadratic time. Right, so these effectively do the exact same thing. We're inserting n elements into priority queue and removing those n elements in order. We can either keep the list unsorted, however, that means that remove min will take linear time each time we call it. On the other hand, we could keep the list sorted. Our inserts would take order n time, but our remove mins would be constant time. Right, so what does that look like? Well, if we're going to keep our list unsorted, then actually our PQ sort becomes equivalent, analogous to a selection sort. So we could think of selection sort as a variation of PQ sort. Let's try to remember what selection sort is like. You'll recall that for selection sort, you're actually, each time you're moving across let's say there's an array, where you're moving across that array, each time selecting the correct next element to put in order. So for example, we're at the beginning of our array. We want to make sure that that 0th element, the first element within this list that's stored in the array, is the smallest element. We have to compare that first element with all the others to select the correct one and put that at the first entry. Then move on to the second entry. We consider just the rest of the list from the second to the end. We're now looking for the second smallest element. Again, we compare this second one to the remaining n minus 2 element. We select the correct one and put it at the second entry. We do this until we get to the end of the list. Each time we're actually looking at a smaller and smaller part of those elements stored in the array. But at the end, we will have our sorted list. So that's how selection sort works normally. We should have come across that before. So if we're keeping an unsorted list, then when we're doing our inserts, that's constant time. We're simply inserting at the end of our list or at the beginning. It doesn't matter. However, that remove min part is equivalent to a selection sort. Why? Because each time we want to remove min, we scan through the entire priority queue and have to select the correct one to pull out. Each time that we do this, there are fewer and fewer elements, so we are comparing fewer and fewer elements. So it's actually the same as our selection sort. How long will this take? Well, the first phase, that is simply doing these n inserts, each of which are constant time, will take order n time because there are n of those inserts. Then our second phase, now this is where we have the issue, because each of these can take worst time order n, but we realize that the list is actually getting shorter and shorter. So we end up with, at worst case, initially n minus 1 comparisons, although we're comparing that first one to them, so it'll actually be n operations. Then, because we first assumed that first one, so we're actually considering all n of them. Then, in the second step of the second phase, we look at the remaining n minus 1 element. Then the third step, the n minus 2 elements, and so on, until there actually is only one remaining element within our priority queue. We then remove that, because that is obviously the minimum priority one. So if we count these all up, there'll be n operations plus n minus 1 operations plus dot, 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 all the way up to plus 2 operations plus 1 operation. We've seen this series before, certainly. We discussed its origin. We can add or fold. So we can add the series to itself. We can fold it in half. We end up with, if we're adding it to itself, n terms, each equal to n plus 1. We divide by 2 to get the original series. And so on the right there, we have our usual n multiplied by n plus 1 over 2 for adding up the terms 1 up to n. That is clearly a quadratic expression. And so we drop lower order terms, we drop constant multiples, we end up with this runs in order n squared time, because phase 1 runs in order n time, phase 2 runs in order n squared time. Overall, we end up with a quadratic function. Right, does that make sense why this is the case? As always, please, if it doesn't, just put a comment or a question there in the chat. We should understand why this is, because for each of these, all right, there's a question. Can't we remove without sorting? Well, how do we remove the minimum? How do we know which one is the minimum? We have two options. We're either going to have to keep them in order as we insert them, or for this particular case, we're keeping an unsorted list. So you actually cannot be able to call remove min without knowing which one of them is the minimum. Okay, we don't have a general remove method within this ADT. It has remove min. And to be able to figure out which one is the minimum, you have to compare all of them to find that minimum. Worst case, there'll be n operations. Then you can return that. Yes, we don't have a search method, right? Thus far, we have said that the methods are insert, remove min, and we kind of mentioned min as well. Essentially, we are doing a search before we remove, right? Because we need to, so we could say in this case, remove min happens to be equivalent to a search followed by a remove of the item that was returned. Oh, that search is more like a min-max function that we've done before. In this case, a min1. All right. Great. So what would this look like? So this version of a priority queue sort that keeps an unsorted list, we said is actually equivalent to selection sort. And so what would that look like? To be able to use this priority queue to sort, we said we first empty the elements from our sequence into that priority queue. That would be the phase one there. So for each one, we're simply taking whatever the next element in our sequence is and putting in the priority queue. Note they're in no particular order in that priority queue. 7 is inserted there, then 4, it's kept in that order. Each one is done like that. Each of those is constant time in that phase one. At the end, we end up with a priority queue that has the same elements as our sequence. They're not kept in any particular order. Then phase two, each time that we call remove min, it doesn't simply go to our priority queue and take out any arbitrary element or the first element. No, it has to find which one the minimum is. And so it has to do that scanning across the entire priority queue. So for the first one, it actually goes and does 4 comparisons. First assumes 7, then compares to 4, compares to 8, compares to 2, then returns 2, which is our minimum. Actually, no, it would have to go across the entire one, right? You can't know that 2 is the smallest one. So continue going to the end, then we return that 2. Same for 3, then the next. Each time we call it, we're actually scanning through all the remaining elements, returning that minimum. So at the end, look, we do end up with a sorted sequence. Because the sequence is first emptied into the priority queue, it is now the elements are emptied from the priority queue into the sequence. By calling remove min, that will return them in ascending order. So it does indeed work. We should understand the first phase will be order in time, linear time. Second phase, quadratic time. Overall, quadratic time. Okay. Then what if instead we keep our list sorted? We actually find that this is equivalent to insertion sort. You'll remember what insertion sort was. It actually came up in our discussion earlier. We said that if we have elements in a list, for insertion sort, we will keep the left part of the list sorted. So not quite the same as our selection sort, where we scan through the entire list each time, putting the correct one in the next space. Now we simply keep the left of our list sorted. What is the left part? We begin with our cursor at the beginning of the list. We then move it one to the right. That considers only the first element. It is sorted. Then we consider the next one. We may have to do a comparison of both of those to be able to figure out which one is smaller and perhaps move that one to the left if the second one is smaller than the first. Then next step, we now are looking at 3 elements to the left of our list. That new element that is being considered has to be put in the correct place, inserted in the correct place. It may take up to 3 now comparisons and 2 moves to put it in the correct place in the worst case. Each time we're considering a larger and larger part of our list. Each time they move one to the right, the new element has to be put in the correct case, in the correct place. So we consider everything to our left. What is to our left grows each time. All right. So now that first phase takes, well, let's look at the steps. First step takes just constant time, takes a single operation. It's already sorted. The next one can take up 2 operations for us to compare and then move that thing. Then the next one 3, the next one 4, the next one 5. At the very last, when we look at the nth element, it has to be compared with everything else. And so we end up with that n operations. Again, we end up with an equivalent series, though now it's in the opposite. It's now ascending instead of descending. So the elements under consideration grows instead of shrinking. And so we end up with that same, though because addition is commutative, the same series. So we end up with the same expression, and that is quadratic time. Then removing them from this sorted PQ, priority queue, because they're now kept in sorted order in a priority queue, remove min runs in constant time. We simply remove the next one because we've kept them in that order. N of those operations takes linear time. Phase 1 now takes quadratic time. Phase 2 takes linear time. Overall, we have that big O n squared time. All right, so same runtime or asymptotic runtime. However, we see that depending on our implementation, whether we're using, right, we said with this case, we're using a linked list, whether we're keeping that list unsorted or sorted, that will determine how long phase 1 takes and how long phase 2 takes. But we see that overall it takes the same amount of time. All right. So what would that look like if we were to now use that sorted list? Note on the right there, inserting 7 takes a single operation. So that's actually the same as it was before. However, when we insert 4, we don't just put 4 at the end. We actually compare 4 with what's already in our list. And so we have to do that comparison. And in this case, put it to the left of 7. Then when we insert the next one, which is 8, we compare it to everything that's in the list, put in the correct place, position there on our very end. Then for each one, we're doing the same thing. Each time we're comparing whatever's in the list. Worst case, for the very, very last insert, that'll be all the n-1 elements compared to its nth element. And so overall, worst case for any of these inserts is order n. There are n of these, we end up with something that's quadratic time because we have that series 1 plus 2 plus 3, or they're up to plus n. Phase 2, remove min simply removes the thing that's at the beginning of our list. We've kept it sorted. So those are constant time. So you see each one there, we're simply removing the first one. We end up with our sequence containing that sorted list. And so we have done the job that we wanted to do. How long would this take? Phase 1, quadratic time. Phase 2, linear time, overall quadratic time. So granted, it's not the very best sorting algorithm. We looked at things that are better, like merge sort and quick sort. Rather, you have come across those before, but it runs in quadratic time. It's equivalent depending on the implementation, or rather the logic of what we keep. Sorted or unsorted the list, it's equivalent to either a selection sort or an inserting sort sorting algorithm. Now, the rest of our discussion is really looking at, can we make this better? Can we improve upon this? By looking at different ways of storing a priority queue, we see that we actually can improve upon this quadratic time sorting method. Right. But first, we just note that you don't actually have to use both a sequence and a priority queue. You can do an in-place sort, whether that's an insertion sort or selection sort, by simply considering the list itself, the sequence itself, to be the priority queue, and simply consider a larger and larger part of it. All right, so instead of using external data structure, we can implement the selection sort as an in-place sort. A portion of the input sequence itself then serves as priority queue. And so we are now simply keeping the left part of that sequence sorted, as the left part of it represents our priority queue. Note as we move our cursor from left to right, the initial sequence is getting smaller and smaller. The part to the left of which represents our priority queue is getting larger and larger. All right, so that allows us to be able to do an insertion sort in place without now needing to have 2 different data structures. That means that actually at the end, we end up with the priority queue being the sequence that is already sorted, but we're looking at a larger and larger part of it until the end there. Okay, and now, so we'd have to do swaps instead of actually modifying the sequences in, instead of emptying it out into priority queue, then putting it back into the sequence. So what does this look like? At the beginning there, we have what would be our sequence. It's all blue. None of it represents our priority queue yet. Then we start moving from the left to the right, considering a larger and larger part of it as the priority queue. So initially, we just consider 5 as the priority queue. It's, the simplest list that has a single element. It's already sorted. Then we consider the next one. So now we're considering both 5 and 4. We see that actually we have to move 4 one to the left to have that priority queue remain sorted. Then we consider the 2. Oh, we actually have to move this twice to the left. We have to do 2 swaps to keep it in order. We keep doing this each time. If you look at the overall graphic, we are increasing the size of priority queue by considering 1 more elements within our sequence, and where necessary, actually doing those swaps. Because the sequence happened to be in reverse order initially, it'll be the worst case. For each one, we'll have to do the number of swaps equivalent to the number of elements that are now in our priority queue. At the end, we end up with this entire sequence being our priority queue. So the second last representation there, we end up with the entire thing representing our priority queue. And in that case, it is now completely sorted. So when we consider that our sequence in the last step, it is sorted, which is exactly what we wanted. All right, so to do this improvement that we would like, we will have to find better and better ways of, or rather quicker ways of doing our insertions and our remove min. And to be able to do that, we actually have to introduce a new ADT, which is called a heap. All right, so what is a heap? All right, before we continue, we have a hand raised. All right, so the person that raised the hand, you can simply type in the question or unmute your mic and ask it. We have another one. So for this sort, we can assume that there will be no repeated values and we only compare previous values with the next. There can be repeated values. Remember, we said that our priority queue does not have to have unique keys. We are now using the element values as our keys because we want to actually use the priority queue methods to sort a sequence of values. So because we can have repeated keys, we can insert values that have the same value as in our equivalent when we run them into our comparator. And so we can have repeated values. Just think of your min method. By convention, you are either checking if something is smaller than your current min, which means that you will only update the min if the new thing that you're considering is smaller than it, which means you end up returning the first, if your min is repeated, you'll be returning that first occurrence of it. If, however, instead you're looking at everything that's less than or equal to your min, and then updating the min each time, then you'll end up taking the last occurrence of that min. It's fine. We don't have an issue either way. Right. And see, note that someone else had a question. They can just type it in there unless it's that same question that they asked before. Right, so what is a heap? This new ADT that we're introducing. Okay, so we actually have a question here. What is being compared, the key or the value when removing? Good question. Taking the last occurrence will technically take more time. Yes. No, actually not more time. Okay, the update. So that single operation, yes. However, you are going to have to scan through the entire list to make sure there isn't something smaller. Right. So the question was asked, what are we actually sorting here, the keys or the values? Let me just go back to that slide to kind of, yes, it was, that one was not, yes, we hadn't talked about anything for that. So whilst a priority queue stores entries that are key value pairs, if we want to use a priority queue to sort a sequence of elements, we will use the element values as our key. Why? Because a priority queue compares keys to determine what the minimum priority is. And so we're actually kind of using it in a way that it isn't intended by, not the way it isn't intended, but simply to achieve our ends by storing our values as the keys. So note at line 8, where we're doing that p.insert, we are passing it e and a null reference. So we're saying we're going to store the element e from our list as the key, and we're not going to store a reference to a value because we're actually trying to use a priority queue to sort a list of values. So we insert our values into the priority queue as keys because priority queues work on the keys. They don't consider the values, they consider the keys to determine which has the lowest priority. And so instead of actually having some more complex method of determining priority and then calling a movement to return the thing that has the lowest priority, like in an actual case where we would need a priority queue, like the examples we looked at, where you perhaps are matching sale and purchase offers for shares, where you are trying to take passengers that are on an overbooked flight and determine who should have the next opportunity to join the flight. Those you would actually be using a key that represents, their member status and some other complex things that allow you to be able to compare two passengers. But in this case, we're going to use it to sort by storing our values as the keys and no values. All right. So what is a heap? Well, a heap is a binary tree. We are comfortable with that. It stores keys at its nodes, and it fulfills or satisfies the following properties. Heap order, which says that for every internal node other than the root, the key of the current node will be larger than the key of its parent. Okay, we can't do this for the root because the root doesn't have a parent. What we're saying is essentially at each level, as we drop down in depth, each subsequent child, grandchild, great-grandchild will have a key greater than its parent. Right? So straight away, this should tell us that at the end of the day, we're going to end up with the root having the minimum key, because its children have to have keys that are larger than it. Their children have to have keys that are larger than the children. The great-grandchildren have to have keys that are larger than the grandchildren. Each node within our key, besides the root, will have a key that is greater than the key of its parent. Right. It's also a complete binary key. A complete binary tree. We haven't discussed this concept just yet. I did talk about like a full binary tree where each level within our tree, so at each depth, we have the maximum amount of nodes. This is very close to that. What it says is that at each level, we'll have the maximum amount of nodes, except possibly the last one. So at all the depths, we have a tree of height h. At all the depths from 0 up to h minus 1, so from the root up to the second deepest level, we will have the maximum amount of nodes, but possibly at the last one, we won't. Right. And this question, does dynamic array get created on a heap? I'm not sure what you're referring to there. Dynamic arrays, as in our global arrays, do they get created on a heap? We will see that we can store heaps in arrays, as we've seen that we can store trees in arrays. But our dynamic arrays, well, we know that the underlying data structure is actually just a normal array that simply gets replaced each time that it's about to be full. All right. So those are the two properties. It has to have heap order and has the maximum amount of nodes, except possibly at our lowest level. All right. And at depth h minus 1, so at the last one, the internal nodes are to the left of the external nodes. Okay, just note we had discussed this. Right. So follow up that in computer science, second year, Prof. Coulter said that dynamic arrays are allocated on a heap, if I remember correctly. Right. Well, I guess that would depend on which particular language. Prof. Coulter, so I'm guessing we're talking about ComSci 1. So there you were discussing what, C++? Yes, that may be true for C++. All right. So note that at each depth, if we start at the top, our root being 0, and then working down the next level, so the nodes that have depth 1, and then depth 2, depth 3, for each of those levels, we have 2 to the power I nodes. So the first one, we have exactly 1 because 2 to the power 0. The next one, we have 2 to the power 1. The next one, 4. We have that maximum amount of nodes, except possibly at the last level. There, though, we'll have the internal nodes to the left of our external nodes. Okay, what does that look like? Well, here we have the maximum number of nodes in our first level, so at depth 0. Then let me actually annotate this so we understand. Right, so here we have 2 to the power 0 nodes. Here we have 2 to the power 1 nodes. The third level, so at depth 2, we could have up to 2 to the power 3 nodes. However, no, sorry, 2 to the power 2. However, this one doesn't have to be full, though the other condition is that the external nodes, rather, our internal nodes will be to the left of our external nodes. So we're filling up from the left. We couldn't have one here and not have one here, right? We're filling up from the left. So that's how we have one here when we only have 2 of them. We wouldn't end up with the 2 being over here and nothing being the children of this one. All right, is this an example of a complete binary tree? Yes, it is. All right, at each level, we have the maximum amount of nodes except possibly the last level. And for that one, we fill up our nodes from the left. And this observes both those properties. And the initial one, the heap order, well, let's see. Or rather, the root doesn't have a parent, so we can't consider it. But for every other node, its key must be greater than the key of its parent. 5 is greater than 2, check. 6 is greater than 2, check. 9 is greater than 5, check. 7 is greater than 5, so heap order is preserved here. All right. Now we want to say that a heap storing n keys has height order log n. We actually looked at this when we were talking about a full proper binary tree, but here we're simply talking about a complete binary tree. So it has the maximum number of nodes at each level except possibly the last one. And we're saying for that one, it also ends up with order log n. It has a height that's order log n. So let h be the height of a heap storing n keys. So it's a heap, so we know that it has to have the maximum number of nodes at each level except possibly the last one. So each of these will have the maximum number of nodes, but perhaps that last level will not. Each of these are actually, and so it goes. So the depth here is 0, then 1, then 2, and we end up with 2h minus 1, right? And we end up with how many nodes at each level? Here in that first level, so at depth 0, we have 2 to the power 0 nodes, then 2 to the power 1, then 2 to the power 2. Then at the last one, something less than or equal to 2 to the power h minus 1, right? Because that one doesn't have to be full, doesn't have to have the maximum amount of nodes. So, but what we'll note is that it actually has to have at least one, right? Or else it isn't the next level. So what we end up with here is that since there are 2 to the power I keys at each depth, and at least one, so at least one, so the number at this depth, I don't know where I'll put that, maybe ND, is greater than or equal to 1, but less than or equal to h minus 1. The number of keys at each depth will be, well, here there's 1, then here there's 2, then here there's 3, so on and so on and so on, until 2 to the power, oh, sorry, I did that incorrectly. Sorry, this should be h, apologies. Right, the entire thing is the height, so that's h minus 1. Okay, so each time we're adding that 1 plus 2 plus 4 plus 8 plus plus plus, the second deepest level will have 2 to the power h minus 1 nodes. Then the next one will have at least 1. Right. Then we've seen something close to this series before. We've counted up numbers from 1 up to 2 to the power h. This is very similar. We're simply going up to h minus 1. We said that this can be represented as a binary number that has, in this case, h minus 1 ones. If we were to add 1 to that, which we actually have in this case, we end up with this number, 1 followed by h minus 1 zeros, and that's just equal to 2 to the power h. All right, I don't have to actually subtract the 1 this time because there was a 1 there in my series. So I end up with this 2 to the power h. And so I end up with an n that has to be at least 2 to the power h. We also know that it has to be less than 2 to the power h plus 1 minus 1, but this is all we're concerned with over here. If we then solve for h here, we'll end up with h being less than or equal to log n. How do we do that? We can take the natural log of both sides as long as those are positive numbers. So if n is greater than 2 to the power h, then that tells us that log n is greater than or equal to log 2 to the power h. Well, remember our log rules that this is equivalent to h log 2. We're in computer science, so the base of this log that's not actually written there is this 2. To what power do we have to raise 2 to get 2? Well, that's 1. So we end up with h this side and log n that side. Right. So you prove right there that this heap will have a height that is order log n. And that tells us something important. Because we'll see that when we are actually inserting or removing min from priority queue that's stored in the heap, we're going to have as many operations in worst case as the height of our tree. That's why I want to get an idea of what this height in the worst case will be, or rather what is the order of magnitude of this height. We find that it's order log n. This is actually what we had before that I was deriving, that at each depth here, we end up with 2 to the power that depth number of nodes, except the last one, which has to have at least 1 node. We add those up together, right? This part is equivalent to 2 to the power h minus 1. We're adding 1, so altogether that's equal to 2 to the power h. All right, and that tells us that n is at least that. We solve for h, we end up with h is less than or equal to log n. All right, so the height is then order log n. In our worst case, it is log n. So we can actually use this heap to implement our priority queue. We'll then store at each node within this heap, which is simply the binary tree that adheres to these properties that we discussed now. Each of those nodes within that tree that is a heap now will store that key value pair. So a key and element item at each node, and we keep track of the very last node, where our very last node is. All right, so it looks something like this. We have here a tree. Is it also a heap? Well, let's see. 2 doesn't have a parent. 6 is greater than 2. 5 is greater than 2. 9 is greater than 5. 7 is greater than 5. All right, our heap order is adhered to. Is it then a complete binary tree? Well, we do have the maximum number of nodes at each level, except possibly the last one. So we're happy with all of that. All right, so this is a heap. We are storing key value pairs at each node within our heap. And we'd want to keep track of this last one. All right, we'll see now why we want to do that. So keeping track of that very last one, our method then to insert items into this priority queue will now be equivalent to inserting a key k to our heap. And insertion consists of 3 steps. We're going to find the insertion node z. So we want to find out where should we insert our new node. We know that we have to keep that heap property that our external nodes are to the right of our internal nodes. So let's say we have a heap that looks like this. All right, this would be our last node, and we want to insert here. okay, rather than somewhere like here or here, because if we were to do this instead, it would no longer be a heap. So we want to insert at the correct place. So we keep track of the last one. We have to find out where should we insert the next one using that last one. We will then store our new key at where this is supposed to be at location Z, at node Z. And we may have to do some operations to restore the heap property, because putting it here does keep our one condition that we have to fill up from the left, that our external nodes have to be the right of our internal nodes. However, it doesn't tell us the heap order is preserved. So we actually have to check, compare this node's key to its parent's key, to that parent's key, to that parent's key, possibly up until our root, to make sure that this key, what's stored here, is greater than what's stored here, and that's greater than what's stored here, i.e. that our heap order is preserved. Right. So here we have example of a heap, the one we've been discussing up till now. We have to make sure that we're going to insert at the correct position. Then we insert into that. In this case, we're inserting 1. We can't simply leave it at that. We have to make sure that heap order is preserved, which means that we have to compare what is now stored here with the key of its parent, with the key of the next parent, and where necessary, swap what is stored at each of those nodes. We call this an upheap operation. So after we insert this new k in that position Z, so in the correct place within our heap, the heap order property may have been violated. We have to then do this upheap that reorders the heap, that reorders the elements in our heap to ensure that the heap order property is preserved. We may have to swap all the way up to the root. And we actually just saw that what is that height? The height is worst case log n. So we have to do worst case log n operations once we've inserted this new element in the correct place. So upheap terminates when either key k reaches the root, so it's actually smaller than all of its ancestors, or it reaches a parent that has a smaller or equivalent key to k. Then the heap order property is preserved, so we can stop our swaps there. Worst case, this would be going up to the top of the root, so traveling the entire height, and so that is worst case order log n time, because it has to be those log n swaps. All right, does that make sense? So we had inserted 1 over here, all right? We have to compare that to its parent, and then the next one to the parent of that, and the parent of that, each time swapping where necessary until we either get to the root or we get to a parent that has a smaller equivalent key, because that will preserve our heap property, our heap order property. So we compared 1 to its parent 6. The parent does not have a smaller or a key that's either smaller or equal to 1. So we swap these two so that here the heap order property is preserved. 6 is indeed greater than 1. Then we compare 1 to its parent, its new parent now. We see that actually the parent still has, this new parent still has a key that is greater than the key of the current node under consideration. So we do another swap over here. And because we've gotten to the root, right, we stop either when we get to the root or a parent that has a key that's smaller or equal. Because we've gotten to the root, we stop our swaps. We did, in this case, travel the entire height. So it's that worst case, it's order log n operations. And now the heap order is preserved. 1 is smaller than 2, 2 is smaller than 6, it works. Right, did I skip on there? No. All right. Then what about removal from a heap? So we now know how we could execute our insert method, inserting into our priority queue that we're storing in this heap. However, how do we execute the remove min method of our priority queue? Now that it's stored within a heap, the remove min is pretty simple. The root will store the key value pair with the smallest key. And so we just want to remove what's at the root. However, if we remove that root, do we still have a heap? No, we've actually destroyed our heap and turned it into 2 heaps. Let's say we had that one that we had before. we had 1 here. Remove min is just removing that 1. However, if we remove this, we don't end up with a heap. We end up with 2 heaps, 1 here and 1 here. So instead of just removing what's in the min, we're actually going to replace what's at the root with what was at the last node W. Then we remove that W, and we may have to reorder our heap to be able to keep our heap order property. What do I mean? So instead of just removing 1, and I believe there was a 9 here, instead of just removing this 1, we actually replace it with this 9. Take out the 1, replace what was there with 9, then remove this. That is still a valid heap. However, the heap order property may have been violated. That 9 may be greater, the key 9 may be greater than that of either child or both children. And so we have to do some operation now to make sure that our heap order property is restored. So this is that removal. Okay, it was a 7 on 9. We don't just get rid of the 2 and remove that root node. Instead, we copy that 2 because we want to do something with it. We want to return that min. However, we will replace that 2 with what was in the last node, 7. Then we remove the last node. We update our reference to our last node to be the new last node, which in this case is now the one that was to the left of it. It's at 9. But now we have to do some operation to make sure that our heap order property is kept in place. How do we do that? It's now a new method called a down heap. So after replacing that root key with the key that was in the last node, we have to now make sure that the heap order property is preserved. The down heap does exactly that. What it does is we now will go down the children of that root, comparing, and we'll stop when we find a child, or rather that both children of the current node have keys greater than it or equal to it, because then the heap order property is preserved, or we get to a leaf, it has no children. Again, heap order property is reserved. How many times do you have to do this in the worst case? We have to travel the entire height from the root to a leaf. And so again, worst case, this is an order log n operation. All right, so what does it look like? We looked at the first part where we replaced what was at the root with at the last node. We should update what our last node is. But however, before we do that, we want to make sure that our heap order property is preserved. We compare 7 to its children. We'll actually swap 7 with its smallest child. So we swap 7 with 5. Are we done yet? We have to check. Are both children of this current node now having keys that are greater than or equal to it? Or are we at a leaf? None of those is the case yet. So we're going to have to do another swap. Right? So we'll have to swap. I don't know. We have reached that case, actually. Yeah, we're at the end. 7, its children. 9 is the only child. Does have a key that's greater than it. So we can stop there. But how do we update the last node? We said that we will have to update what the last node was after we remove that, or in fact, also after we insert 1, we have to update what the new last node is. And for doing that, we will go up until left child or the root is reached, then go to the right sibling, then go left until leaf is reached. What does this look like? So let's say this was our last node. We actually inserted something here, so we have to update our last node to the new last node where the new insertion should be. That would now be here. How do we do this? We said we go up until we get to a left child or the root, and then we look at the right sibling of that left child. So we go up from here, and then going to its parent. Is this a left child? No, it's the right child of this node. We go up again. Is this a left child? Yes, this is the left child of the root. We look at its sibling, all right? And from that sibling, we go left until we get to a leaf. So we go left once, oh, we're at a leaf. The left of that will be our new node, right? Or rather, our new last node. If that reference was W as in the other example, then that would be our new last node, where we would now do our next insert. Right, so now we want to see, we've discussed this new ADT, a heap, talked about the fact that for insertions and removals in our heap, we may have to do worst case operations that are order log n, because for insertions, we will insert the last node or the new last node as we saw the update just now. Then we may have to do an up heap to make sure the heap order is preserved. That can be worst case, some order log n method that does swaps up to worst case the root. When we're doing our, and in fact, we know we have to do n of those to insert n elements into our priority queue. Then what about remove min? We said that remove min, you simply remove what's at the root, replace that what's at the last node, and you may have to do a down heap to preserve the heap order property. That again, worst case would be going from the root to a leaf. So again, order log n swaps. So now we understand how do we do the operations in a heap. We can use a priority queue stored in a heap to sort a sequence of elements. This is called heap sort. So we looked at priority queue sort, PQ sort, that uses a priority queue sort. If our priority queue is stored in a heap, then this is called heap sort. All right. We want to consider a priority queue with items implemented by means of a heap, so stored in a heap. The space uses order n because we'll need n nodes in this tree that happens to be a heap. The methods insert and remove min take order log n time. Why? Because of that up heap that may be necessary when we insert a new node, and that down heap that may be necessary when we remove min. And the method size is empty and min take order one time. We're keeping track of the size, so we can simply return that is empty, or we check our reference to our root. If that is null, then constant time, we can say it's empty. And min takes constant time. We simply return a reference to what is stored at our root. We're not doing any removal, so again, it's constant time. Now, using a heap-based priority queue, we can sort a sequence of elements in order log n time, and we call this heap sort. Why order log n time? We're going to do n insertions and n remove mins. Those n insertions, each of those are order log n time. So that's order n log n for the insertions. Then our removals, again, each of those are order log n time. We're doing n of those. So the second phase is also now n log n time. Granted, there are two phases that are both order n log n, but we drop constant multiples, so we end up with something that's again order n log n. Have we improved our PQ sort compared to when we were simply storing this priority queue in a linked list? Certainly we have. We saw that with the linked list, either the first phase was linear and the second phase quadratic, or the first phase was quadratic, then the second phase linear. So overall, that was n squared, right? Order n squared. Now I've gotten it down to order n log n. That's much faster than quadratic time. So we have actually improved our PQ sort by storing it in a heap, creating what we now call heap sort, because this runs in order n log n time rather than quadratic time. So it's faster than insertion sort or selection sort. All right, so we developed a brand new sorting algorithm by using a priority queue. We store the priority queue in a heap. We then call that heap sort. That sorting algorithm is faster than the other two that we considered, insertion sort or selection sort. So we can actually store, we now see that we can actually store a heap in a global array. So in a vector of length n plus 1. We use that same rank function that we used when we're simply storing a tree in a global array, right? Because our heap is actually a tree. So for the root, we said that's stored at rank 1. And then for any child, left child is 2 times the rank of the parent, right child is 2 times the rank of the parent plus 1. We realize that we don't actually use rank 0. We don't now have to store links between the nodes, because we know from any key that's stored at a particular rank, we can simply calculate what the rank of its left child and right child should be. So we don't actually have to have that linked structure to create the concrete structure where we're storing this heap. The operations, the insert operation corresponds to inserting at rank n plus 1. So where our last node is simply keeping track of rank n plus 1. That's constant time. Yes, we may have to do some operations to make sure the heap order is preserved, but we can easily insert into our last node. Operation remove min corresponds to removing at rank n. Right, this yields an in-place heap sort. Look at what that would look like. Oh, perhaps I should have just assumed that everybody understood that. The reason that remove min corresponds to removing at rank n is that, remember, for remove min, we swap what's at rank n, so what's at the last node, with what's at the root, so it's at rank 1, and then remove what was at that last node. That's why it's equivalent to removing at rank n. Whereas inserting, it's the new last position, which would be inserting at rank n plus 1. Right, so here we have a heap that is stored within an array. If we wanted to remove min, we'd want to be removing and returning what's stored here at our root. So we'd simply copy this into there, return what was there, and then we have to delete that. All right. If instead we wanted to insert something new, so we had the original list, we'll be inserting at that n plus 1. All right, so we'll be inserting here in the correct place, and that will be the left child of 6, right, which is at rank 3, which correctly would be then 2 times 3, which gives us that rank 6. So we'll insert something there. We see that both those things were true. Inserting is equivalent to inserting at rank n plus 1. Removing is equivalent to removing at rank n. Then merging 2 heaps. Let's say we're given 2 heaps and some other key. We can actually create a new heap by creating a new root, storing k there, and then making the 2 heaps the left and right subtree, or the subtree is rooted at the left and right child of this new root. We then may have to do a down heap to restore our heap order property. What does it actually look like? So let's say we had 2 heaps. On the left here, we have 1 heap. On the right, we have another heap. We said that we have to have some other key k. In this case, that was 7. We create a new root with that key stored at it. That's this. We then root the first heap as the left child of our new root, and then the other heap becomes rooted at the right child of our new root. So this is, well, it is a tree, but it's not necessarily a valid heap. We may have to do a down heap to ensure that our heap order property is preserved. And let's see, is it currently? No, because 7 is a larger key than its children, 3 and 2. So we'd actually have to do a swap here. That gives us this. Then we'd check again, as we do with our down heap, is it now greater than, or rather, is it smaller or equal to the key stored at the children? No, it isn't, so we have to do another swap here. Now after that down heap operation, we have a valid heap, and this heap is actually the result of merging the 2 heaps and using another key, which in this case was 7. Right, so that looked like this. We have to do that down heap, going down, swapping with the smallest child as long as the children are smaller than the parent, until we either end up with a node at a node whose children's keys are greater than that of the one that we're down heaping, or at a leaf. In this case, we end up at that. So what does this allow us to do? This ability to combine 2 heaps actually allows us to be able to construct a heap in what's called bottom-up heap construction. right? Recall that for using a heap, storing a priority queue to sort a list of elements, we have to insert those elements, all of them, into our priority queue, which is in that heap, then call n removement operations. Well, that initial phase, the insertions, that was n insertions, each of which is worst case order log n time because we have to do those down heaps. So all in all, that first phase is order n log n time. We actually that we could improve upon that time by, instead of doing a series of n inserts, doing what's called a bottom-up heap construction. We'll see that this actually ends up with order log n time, which is better than order n log n. All right, so how do we do this? So in each phase, we have pairs of heaps with 2 to the power I minus 1 keys, and these are merged into heaps with 2 to the power I plus 1 minus 1 keys. Don't worry about what that actually would amount to. We're going to look at our example to see exactly what that is. So what it's saying is that we're going to have a series of phases, log n phases. At each time, we're going to have 2 to the power of I, or rather heaps that have 2 to the power I minus 1 keys, and we're going to merge those. So initially, we have at phase 0 heaps with simply 1 node each, and we're going to keep merging those into larger and larger heaps. What that look like? Well, we're going to have some amount of heap with a certain amount of nodes, initially 1 at each phase, a greater and greater amount. We're going to merge these by using another key and doing this combining or merging of heaps that we just looked at now that may need a down heap as well, right? So this is how this would be done programmatically. We're going to come back to this because yes, whilst you may have to implement this for a practical, we want you to be able to, given a sequence on paper, do a bottom-up heap construction. And that's actually what I'd like to spend the rest of the lecture doing, to see how we do a bottom-up heap construction given a sequence of elements. So we'll come back to that. But how we would do this on paper is we'd take, if we have a list, so this sequence of some number of elements, we determine, well, which of those elements would make up the lowest level of our heap. Then we'd simply put those in the order that they appear. They're not in any specific order at the bottom there. They're simply in the order that they appear in our sequence. That gives us a certain amount of heaps, each of which has only a single element. So they observe all our heap properties. Then we will use the next few keys to combine those heaps into larger and larger heaps, right? So at each one of these, we are adding another key. We are making that the root of the new heap, and then we're putting the 2 heaps at the left and right child of that new heap, and we may have to do a down heap operation. So note over here, we'd have to do a down heap operation, right? Because the key there is larger than the key of the children. Here, again, we have to do a down heap operation because 5 is greater than 4. Here, we have to do a down heap operation, and here as well. And in each case, we have a child that is a key that's less than the key of that parent. Okay, so here's what we had initially, and for each of those, we do the correct down heap by swapping the heap, rather the key of the parent with that of the smallest child. 25 gets swapped with 15, 5 gets swapped with 4, 11 gets swapped with 6, and 27 with 20. We now have 4 valid heaps. We'll then take the next 2 elements that were in our sequence and use those to now combine these 2 heaps. All right, so happen to have 7 and 8 as the 2 next elements in our sequence. So we simply create new heaps with those as the root and putting the heaps that we had before as the left and right children of these new heaps. We may have to do a down heap to ensure that our heap property is preserved. And in each case, we have to, because 7 is greater than 4, and also happens to be greater than 5. So we have to do 2 swaps. We swap 7, we swap 7 and 4, Then we have 4 there, 7 there. We then again have to swap 7 and 5. Similar thing happens here, except we only need a single swap. 8 is larger than 6, so we swap those two. We then end up with 2 valid heaps. Heap order property is preserved, and we have that they complete by trees. We now have 2 heaps, and we can use the last element from our sequence to create the final heap that is the merging of these 2 heaps. That final element happened to be 10. We then create that as the new root, merge the 2 heaps, and we have to do a down heap to make sure the heap order property is preserved. We swap it with its smallest child. That then gets compared to the 2 children of the new node. Again, a swap has to happen here and again here. We end up with then this final heap. So what were we doing? And how is that actually different to what we were doing before? Well, to create this heap, we could have either done what we described in our first discussion of heaps just now, that we would do n inserts, each of which would need up to log n time to do the down heap. Instead, now we are doing a bottom-up heap construction, and we see that we didn't do n operation. We actually did log n of these merges, each of which, granted, has its own down heap that's order log n. However, there are far fewer of those compared to if we were doing n successive inserts. All right. So the worst case time bar down heap is again that order log n. All right, there's a question, or is it the one that's already been typed in here? Where did 10 come from again? 10 came from the sequence. Each time we are using up elements that were in our initial sequence that we are trying to sort. And remember, the whole point is that we're trying to use this priority queue to sort a sequence of elements. We would empty that sequence into our priority queue and then call remove min n times to get the proper sorted order of it. All right. So each of these nodes is traversed by at most 2 proxy paths. Okay, this is quite a simplification, or rather a shorter explanation of what's in the text. You can take a look at that. That shows that actually with this bottom-up heap construction, we will at worst have to traverse each node. So we'll be passing each node, I believe, twice as we're looking at those paths. And so our bottom-up heap construction runs in order n time, and that's better than the order n log n time that we had before. So a bottom-up heap construction is faster than n successive insertions, which would each take order log n time. And so this now speeds up the first phase of our heap sort. So we're able to now have a heap sort that has 2 phases, or rather a sort that uses a priority queue that has 2 phases. The first of which will be order n time, the second of which will be order n log n time. We still end up with something that's order n log n time, but we have made this part go quicker, and what we end up with is still something that's significantly better than our initial PQ sort that was order n squared time. All right. And this is showing that those proxy routes that would end up touching each node at most 2 times. That's how we end up with that order n, that linear time method for a bottom-up heap construction. All right, so before we actually take a look at a couple more examples, I'd like to make sure that we're all on the same page with that. We can take a look at what the algorithm for this is. So if we're to do this programmatically, what you'll be doing is you actually start with that sequence S, and we have a recursive function that will, for its base case, simply return the node itself. But then for any other case, we'll recursively call the bottom-up heap construction on on a list that's actually, or rather on a heap, that is splitting that list into. All right, so we start with a list storing a certain number of entries. First, to be convenient, it has to be a number of entries that is some power of 2 minus 1. So it's that full binary tree that we've looked at. Okay, it'll work even if there are fewer than this at the bottom there. We will then take some node from this. Let me show you, let's say this is actually in a sequence. Okay, a sequence of elements. Let's say this is E1, 2, 3, up to En. What we'd actually do is we'd take this element, would make that the root of our new heap, and we would want to create a heap out of this half of what's left and this half of what's left. Right? So we're going to remove the first one, then we split our list into two lists, L1 and L2, which are each half the size of what was left. We removed one, and then we half that to end up with these two lists. We're going to recursively call bottom-up heap construction L1, L2, so they should actually return to us two heaps. And then we're simply going to create that new heap by storing E as our root, that E1, and then making its left and right child those two valid heaps that were returned to us. All right. Programmatically, it seems simple enough. You're simply recursively calling this method on successively smaller and smaller sequences. In the case where you simply have one that has, let's say, 3 elements there, you'll take this one as the root and you'll recursively call it on these two. Each of those are the simplest type of heap. They have a single element. They are valid heaps, and they'll create this E1, whatever was there, whatever was there. We may have to call down heap. So here we do perform down heap to make it a valid heap. This is returned to whatever iteration called it. So that will take this and another one like it and create a new heap by having whatever its lowest value was, its first one in its sequence as the root, and then creating a new heap with that as the root and doing a down heap to make sure the heap order property is preserved. Then whatever called it will do the same thing with 2 of those. Okay, and so this will build up your heap programmatic. Will require you instead be able to do this given a list to be able to do this on paper. All right, so if you give me a second, I'd like to just consider a previous assessment that we had, and we'll look at how we'd do that on paper together. Are there any questions while I'm doing that? Please put them in the chat and I'll address them. And I think actually let's use last year's main exam paper to do this. Right. I don't see any questions besides one that's asking about prac. Do we have a prac this week? Yes, we have a prac this week. We'll have a prac each week that we're not having an assessment. I don't believe there are actually any public holidays that fall on Thursday. So you are going to have all of your usual pracs each week, except when you're going to have semester test 2 as well. All right, give me one moment. I just have to swap over to my machine to upload this, and then I'll be back. Oh, no question. Topic trees will be the topic of this week's prac. Okay, and I'm back. If there are any questions while I was, excuse me, while I was uploading that, please just type them back in as they get cleared each time that I come in and out of the session. While I wait for that, I will. Would it be possible please make our project file submission? Let me go back to that. That went off. Viewers can't remember the details. Okay. I'll inquire Prof. van der Hart as a way to make those visible to all of you in general. In the meantime, you can just send me an email and I will do that. And actually, the reviews are all done, so we'll also have to find some means of sharing that within the next day or so. Simply that Eve has a limitation on the size of the field in the mark sheet, so it won't be easy to do that using what we have on Eve right now. All right, but we can continue that discussion tomorrow. I would like to look at a particular example. All right, and this shows you the type of question that you're going to get. So therefore, question 4b, illustrate the execution of a bottom-up heap construction on a heap. Let me just zoom down a bit. You can also set your own zoom level so you can see it properly. Bottom heap construction of the following sequence. You need to provide a graphic representation of the heap at each stage in the construction, including any intermediary operations or intermediate operations. You see, if this is for 10 marks, it's actually quite a few marks for what is required. What you have to do here is to take the sequence and create a heap from that using a bottom-up heap construction. Now, as I said, programmatically, what's going to happen is that you would take this first element, then break up the list into two however you could, and recursively call bottom-up heap construction or bottom-up heap on that. When we're doing it on paper, we don't do that same thing. When we're doing it on paper, we instead take the elements as they appear here and build up our heap from that. All right. You should first check that it is some multiple, or rather some power of 2 minus 1, so that you understand how many nodes you'd have to have at the bottom level of your heap. You'll have one more than the rest of the heap. It is if it's full. If not, then you'll have to have a certain number fewer. So let's see how many we have here. We have 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 15. So this is what, 2 to the power 4 minus 1. So I know that half of those, and actually the greater half of this, should be at the bottom. So I'll end up with, it is a full one here, I'll end up with 8 at the bottom, and then the other 7 will be used to combine my heaps into larger and larger heaps. So what that look like, I'm going to draw it on here, so I have to switch from the whiteboard to this. And there's certainly enough space, but you'll be doing a different representation. Okay. You will then be doing a different drawing for each step that you take. Okay, let me do it there. All right, so I begin by starting with those 8 as heaps of only 1 node each. So I'll have here 17 over here as 1. I will have 6. I will have 12 and 22. I'll have 15 and 27. And finally, I'll have 8 and 20. All right, these are trivial heaps. They only have 1 element each, but they are all valid heaps. All right, then I will combine. So I've taken all of these, and I want to now combine those into larger and larger heaps using the elements that are left in my list. So to combine these 8 into now 4 heaps, I'll need 4 other elements to do that with. I'll take these ones. So I'll put here 32, 19 and 42, and 14. Now, for some reason, year after year, we get that students would now want to keep combining at this stage. You can't do that. At each stage that you combine, you have to do a down heap to make sure your heap property is preserved. If you simply combine them all into a single heap, then try to do a single down heap operation at the end, you won't end up with the correct heap. So here, what you need to do is for each of these new heaps to be combined using a new element k, you have to compare the now root of this heap with its children to make sure the heap property is preserved. We'll see that we actually have to swap 32 and 6. We have to swap 19 and 12. We have to swap 42 and 15. We have to swap 14 and 8. And for each one of these new states, you actually get a mark for that. So you have to show them. So for the next set, I'm going to end up with 6, 17, and 32. As my first heap on the left there. Then I end up with 19, 12, and 22. All right, then I end up with 15, 42, swap that with its left child, and 27. And of my last heap, 8 has been swapped with 14. And 20 remains the right child. So now I have 4 valid heaps. I want to combine each of those pairwise into larger heaps. Okay, there's a question about how many to choose. I'll address that once I'm done. So I take these next two, 31 and 10. And I have to now do that down heap again for each of them. I see that 31 should be swapped with 6, and then actually swapped again with 17. I see that 10 should be swapped with 8. And I can actually stop there on that one. All right, I should redraw this, but just in the interest of time, since we still have another question to address, I'll just show it over here. You have to redraw it, you get a mark for it. 6, 17, 31 is what I end up with there. 8 and 10 there. All right, then that being the almost penultimate state of my heap, I will insert, or rather create my final heap by using the last remaining element as my root and combine the other two then as its left and right child. I then have to do a down heap. I see that 32 is greater than the key stored as its children. I'll have to swap that with that. I then consider its children. I have to swap with the smaller child. I then check, is 33 smaller than its children? If it is, that's fine, but in this case, it actually isn't. 33 is not smaller than 1922. I swap with the smallest child. So what will I end up with? I end up with a 6 over here, a 12 over there. I end up with a 19 over here, and a 33 at the bottom there. All right. Again, you should actually redraw each one. You get the marks for showing that. But that is what's expected of you to show as a bottom-up heap construction in or subsequent tests in the exam. I will actually look at another couple of examples tomorrow. Last year, we did a separate video where we were showing the examples and only covered the theory in the class. And we found is that a lot of people simply did not look at that video, and so lost those marks unnecessarily. All right, so I just want to spend a little more time making sure that we're all on the same page on how this is done. All right, now I'll go back to that question. So how do we know we have to choose 8 elements for the leaves of the tree? Well, you recall that I said that for if our tree has the maximum number of nodes, then we're going to end up with something of the form 2 to the power h plus 1 minus 1. We end up with this number of nodes, which is simply 1 less than some power of 2. So I'd look at, well, what's the power of 2 that I'm working with? And that would tell me how many nodes I have at the bottom. If I have exactly a number that's equivalent to this, then I'll end up with simply, let's see, I'll end up with 2 to the power h minus 1 nodes at the bottom, and then half that many nodes each time that I go up. If I find that I have something that lies between 2 to the power h minus 1 and it has to be larger than that, doesn't it? Otherwise, it's simply be. But anyway, and 2 to the power h plus 1 minus 1. And then I would have to have, I wouldn't have the maximum number of nodes at the bottom. So I'd simply have to make it 1 less. So if, for example, I had, let me scratch this out, I had 14 nodes instead of 15, then, okay, it's still close to that 2 to the power 4, right, minus 1, close to that number. I would simply have to have fewer here. I'd have to have 7 there. If now instead I had even fewer than that, I would simply have less and less at the bottom there. If now I end up with something less than, let's say on next power, less than 7, then now it becomes that I have fewer levels there. I'll simply then have, let's say it was exactly 7, then I have to have 4 over here, 2 over there, and 1 over there. So it depends where I'm between. Here I was between 7 and 15. I happened to actually be at the 15. So I knew I'd have, let's see, 4 levels. And if I was between the 7 and 15, I would have 4 levels, but the last level would not be 4. Right? Now that's, that's if we're actually looking at what the maximum number of nodes is for 2 different trees, and we are trying to figure out exactly where it should be. Really, we're not going to give you that many to do. You can easily logic it out for yourself. So let's say you started at the end here and said, okay, this one has to be my root. So that'll be at my depth 0. I'll then need 2 to be the children of that. I'll then need 4 to be the children of that. I'll then need, let's say you had more than these, I'll need another, I jumped there somewhere, sorry. I'm talking about the depths, okay. Then I'll need another 8 to be at depth 3, and eventually you'll have less than or exactly what you need for the last level, and that's how you split them up there. All right, so there is some mathematics to it, but you can simply start from the right and see how many you should go. Now, please re-explain how you choose 8 elements for the leaves. Okay, we choose the first 8 elements. How do I know that I need exactly 8? I think the easiest way is really to, as I've shown, let me erase all this. As I've shown how you could just do it by inspection, by seeing, okay, the last one's going to have to be my root. All right, so I'll need, okay, for some reason that annotation's not happy. All right, there we go. So this is going to have to be my root. That's at my level 0. I'm going to need 2 for its children. Okay, so that's at level 1. I'm going to need 4 for those children. It's at my level 2. I'm going to need then 8 for that one's children. That's at my level 3. And let's say I ended up with like 2 more here. I'd say, okay, those at level 4. So I end up with something that looks like this. 2 of these, I would combine those together with the next 8. Then the 4 that I've shown here go there, 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 there. Let me draw these so it's not confusing. That is horrible. Right. Then the next 2 go there and there. And then that last one goes there. So if I start counting from the right, knowing that the last one will be my root, I can see how many I'll have at each level. I think that'd be the easiest way to just do it by counting those up from the right, rather than figuring, okay, it has to be between 1 less than some power of 2 and greater than or equal to some other 1 less than a power of 2, and then I'll see from there. Simply just count them out that way. All right, we'll stop there. It's the end of our period. However, I will do the same thing tomorrow. We'll look at maybe 2 more examples. We'll see how we're supposed to. I'll do it on the whiteboard so we're doing it properly, because it's something that you should understand. It is a very efficient sorting method. You have to understand we're trying to put sequences in a priority queue. We're storing that priority queue in a heap. The first phase is the bottom-up heap construction. The second phase is removing min n times. The first phase of bottom-up heap construction runs in order n time. The second phase, n log n. We end up with something that's overall n log n time. That's a very efficient sorting method. That's the same runtime as quicksort, which is what Java uses for its sorting methods on arrays. So it is a good method. Last question. We should do this question paper thing more often. All right. Well, the ones where you pick up their issues, we will do that. Okay. And in fact, the rest of the the second term, you're looking at different types of self-balancing trees, and we will most certainly go over examples for each one, because there's a large body of theory on how this is done programmatically, but you are going to be expected to do them on paper, and we'll do exactly that. All right, and last question, how's Smith's test marking going? It's going all right. We should be done by Wednesday, so marks can be out by Thursday. Then moderation, and beginning of next term, you will then get your papers back. All right, I'll stop there as we're about to run into the next